In this class, we'll study about aliasing. In the last class, we have seen the concept of sampling theorem. Say, for example, x of d is there. Again, in time domain, the sampled signal is represented like xs of t. Then, what is its corresponding frequency domain representation? Spectrum. The x of omega is the spectrum of the original signal x of t, where xs of omega is the spectrum of the sampled signal. We know that x of t is a periodic signal. Okay, again the spectrum is x of omega, but whereas x of t is a discrete signal, it may be aperiodic, but discrete signal. We know that whenever we have a discrete in one domain, then definitely it will be periodic in the other domain. Okay, as s of t is discrete in time domain, because after sampling the signal will come like a discrete time signal. So xs of omega has to be periodic, because discrete in one domain will be periodic in the other domain. That's why that xs of omega is periodic. It's like the spectrum is going both on left side as well as on the right side. So now again we have seen three condition. Okay, the condition is with respect to sampling maximum frequency. What should be the sampling frequency? Either it should be greater than 2 omega m, or should be equal to 2 omega m, or it may be less than 2 omega m. Okay, again we have seen the separate condition in the separate diagram. And then in that, if omega s is chosen less than 2 omega m, then definitely aliasing will happen. Okay, in the out of three condition, we have got the condition like this, where the high frequency spectrum overlap with the low frequency. Okay, so this is called aliasing. Okay, so then what is actually happening here? Okay, see, this is zero spectrum with 0 and omega m minus omega m. This is omega s plus omega s minus omega m. Similarly here, minus omega s plus omega m minus omega s minus omega m. So like this, you can draw the spectrum with this simple formula, plus or minus n omega s plus or minus omega m. Just by varying the value of n and putting all possible combination of plus 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 minus minus plus minus minus, we can draw the spectrum like this. So in this diagram, if you observe that omega s minus omega m is less than omega m. Okay, if you take that condition, omega s minus omega m is less than omega m, then what is happening? Omega s is less than 2 omega m. Okay, so in case of aliasing, what is the condition we are getting? The condition is omega s is less than 2 omega m. Okay, so if the sampling frequency is less than the twice the maximum frequency of the signal, then definitely the aliasing will be there. Definitely aliasing will be there. So when the high frequency, what do you mean by aliasing? Okay, it is when the high frequency component interface with the low frequency component and appears as a low frequency, the phenomenon is referred to as a aliasing. Okay, so it is the interference of high frequency component with the low frequency component. So the signal is getting aliased. That means again the signal is getting distorted, so that from this we cannot recover back our original signal. Okay, from this excess of omega, we cannot exactly recover back our x of t. That is the problem with the aliasing. Why? Because if you see here, once the finally the signal will go like this. Okay, the spectrum will go like this. Okay, again from this shape we cannot recover back our original spectrum. Okay, original triangular shape we cannot recover. That is the problem of aliasing. How to overcome the aliasing? Okay, so what is the definition for aliasing? Aliasing occurs when the sampling frequency is less than the twice the highest frequency component of the original signal. That means what? If omega s is less than 2 omega m, then definitely aliasing will occur. Okay, then what is the method to overcome the aliasing? Okay, method to avoid the aliasing. So we have to choose the sampling frequency. Definitely to overcome the aliasing, omega s has to be greater than 2 omega m. Then before going to this formula, we have to fix what is omega m. Okay, we have to fix what is omega m. So what we have to do further, to fix omega m, we have to strictly band limit the signal to omega m. Okay, that means what, before passing to the sampler, okay, we have to pass the signal through a low pass filter. Okay, we have to pass the signal through a low pass filter with a cutoff frequency fm, with the cutoff frequency fm. Okay, that means maximum frequency, some maximum frequency. So strictly band limit the signal to omega m. For that we'll be using low pass filter. That low pass filter is also called as the anti-aliasing filter, because by with help of this we are avoiding the aliasing, so that this filter, low pass filter, is called anti-aliasing filter. And then we have to choose omega s strictly greater than 2 omega m. Okay, omega is strictly greater than 2 omega. So method to avoid aliasings, there are two. First we have to fix omega m, then we have to choose fs omega s uh, strictly greater than 2 omega m. So now how to reconstruct the signal from its samples. Okay, so once if xs of t is given, how to recover x of t? Okay, or otherwise in the frequency domain spectrum, if excess of omega is available, how to get x of omega? Okay, because at the receiver side, definitely from the samples, okay, we have to reconstruct our original analog signal. Okay, original analog signal. For that we are using the reconstruction procedure. So once if you are given with excess of t or excess of omega, how to get the x of t or x of omega? Okay, so say the signal excess of t is available. Okay, it is passed through some filter. Say at the receiver side we are using some filter. Say the filter is having transfer function h of omega. Okay, h of omega, then we are getting xr of t, that means reconstructed signal. Okay, see what is actually happening, the xr of t is the signal reconstructed from x of t, which is approximately equal to x of t, which is approximately equal to x of t. So what is actually happening, from x of t, we are getting xs of t. Okay, at the transmitter side, in the receiver side, from xs of t we are trying to recover some signal. Say that signal is xr of t, but approximately xr of t is equal to x of t. Okay, so what is the condition? We cannot exactly recover back our original signal, but approximately we can recover back. Why? Because in the process of quantization and purely if it is digital, again we'll be using quantization technique and all, then definitely we'll lose some information. Okay, so xr of t is the recovered signal from the sampled signal xs of t. Okay, then we can write the h of omega, the transfer function is again in the frequency domain representation xr of omega divided by xs of omega. It's very simple. The transfer function is equal to output spectrum divided by input spectrum, or otherwise what is the spectrum of the xr of omega, that is equal to h of omega multiplied with xs of omega. Okay, so that means what, to get xr of omega, the xs of omega has to be multiplied with h of omega, h of omega. Now what should be the spectral shape of h of omega? What is the mathematical function or mathematical shape of h of omega? Okay, that we have to see now. Okay, what should be h of omega? Again we'll assume that condition, because we want to reconstruct the signal properly. That means definitely uh, at the transmitted side we should have used the sampling theorem properly. That means fs should be strictly greater than 2 fm, or otherwise omega s is strictly greater than 2 omega m. Okay, only then we can recover back easily at the receiver side. Okay, if fs is less than 2 fm, definitely aliasing will be there. if fs is equal to 2fm, again we can recover back, but we need ideal filters. Okay, that is practically not possible. That's why during the reconstruction process, definitely again at the transmitted side itself, sampling theorem, sampling frequency should be much greater than 2fm, strictly greater than 2fm. Okay, so fs is strictly greater than 2fm. Then we know that if fs is strictly greater than 2fm, then what is the spectral shape of excess of omega? Okay, we know that if omega s is strictly greater than 2 omega m, what is the spectral shape? Okay, so again, if it is strictly greater, again there will be a gap between the spectrum. Okay, so this is 0 omega m minus omega m, omega s, omega s plus omega m, omega s minus omega m, minus omega s, minus omega s plus omega m, minus omega s minus omega m. Okay, so now this is excess of omega. That means spectrum of the sampled signal when the sampling frequency is much greater than the twice the maximum frequency of the signal x of t. Again, we know that from this, how to recover back x of omega. We know the shape of x of omega is simply the only one triangular function. Okay, we have started with that. Okay, only one triangular function. So from this train of rectangular pulses, okay, train of rectangular pulses, again we know that the amplitude of this one for all the things, again we can put the central axis here. Okay, amplitude for everything is 1 by ts. Okay, amplitude is 1 by ts. Okay, but again at the transmitted side, amplitude would have been 1. That is very simple, that we can multiply with the ts with some gain constant, but we have to recover back only this spectrum. Okay, so for this we can use low pass filter. Okay, if you pass this excess of omega through low pass filter with the cutoff frequency of this value, then we can get only this spectrum. So the filter is low pass filter. Okay, what is the filter we have to use? Low pass filter. So we have to use a low pass filter like this. Okay, low pass filter. Again, h of omega. Again, the cutoff frequency of low pass filter is omega c. Omega c. That means again we know that omega c has to be greater than omega m, but it has to be less than this one. Okay, your omega c. Why? Because what we need finally, we need only this spectrum, only central spectrum. Okay, we need only central spectrum. Okay, that we'll call it as xr of omega minus omega m plus omega m. Okay, so we need only central spectrum. So we have to choose a cutoff frequency of low pass filter such that it is greater than omega m, less than omega s minus omega m. So what is the main condition here? The cutoff frequency of a low pass filter has to be greater than omega m but less than omega s minus omega m. Okay, then only we can properly recover back our original spectrum. So this is the main condition. Okay, so and also one more thing, to have a gain value of 1 year. Okay, the gain value of low pass filter has to be ts, Why? Because this is 1 by ts multiplied with ts will provide gain of 1. Okay, so this The same operation, see here we are dealing with the frequency domain. Okay, we are dealing in the frequency domain. Yes, again the same thing. What is happening in the time domain? What is happening in the time domain during this process? Okay, why? Because h of omega I can write like h of t, h of omega. If you take inverse Fourier transform, we can write like h of t, again xs of t is equal to xr of t. We know that xr of t is the convolution of xs of t with h of t, xs of t convolution with h of t. Okay, convolution with h of t. So we can write xr of t is equal to xs of t convolution with h of t. Xs of t is the sampled signal. Xs of t is the sampled signal. Again, we know that xs of t can be represented from x of t like this. It means what? Simply x of t multiplied with the train of impulses, summation n minus infinity to plus infinity del t minus nts. Okay, so xr of t is equal to, again that x of t we can take inside. Okay, so summation n minus infinity to plus infinite x of t del t minus nts convolution with h of t, just multiplication operation with impulse. So summation n minus infinity to plus infinite, instead of t we'll have nts, x nts del of t minus nts convolution with h of t. Again, we can apply the convolution operation here. Okay, convolution of impulse with the signal h of t, so that we can write this from summation minus infinity to plus infinite x n t s h of t minus nts. That means this delayed impulse multiplied with, sorry, convolved with h of t. So this is our final xr of t. Okay, final xr of t. So xr of t is equal to finally summation n minus infinity to plus infinite x n t s h of t minus n t s. Okay, we know that h of omega, that means low pass filter spectral shape. Okay, that low pass filter spectral shape, the low pass filter spectrum is low pass filter naturally extending from minus omega c to plus omega c with the gain value of ts. Okay, so that means h of omega I can write like h of omega is equal to ts whenever mod omega is less than omega c. That means when omega varies from minus omega c to plus omega c, we are having value ts 0 otherwise, 0 otherwise. Okay, so the shape of h of omega we are mathematically representing like this. Okay, mathematically we can represent like this: h of omega is equal to ts when mod omega less than or equal to omega c, 0 otherwise, 0 otherwise. So once we know h of omega, with the inverse Fourier transform we can calculate h of t. Again, once if you know h of t, we can calculate what is this value. Okay, so then for this we have to apply the inverse Fourier transform formula. Okay, now we have to calculate what is h of t from h of omega. Okay, so inverse Fourier transform formula one. Okay, h of omega, again e power j omega t d omega. Okay, this is the inverse Fourier transform formula. So h of omega is having value of ts. So ts by 2 pi integration minus omega c to plus omega c e power j omega t d omega. Okay, in ts by 2 pi e power j omega ct minus e power minus j omega ct then Ts divided by 2 pi 2j. And one more thing, when we do integration of this one, we'll be getting some extra factor, that is with respect to, we are doing integration with respect to omega, so we'll be getting by jt in the downside. Okay, so this we can write like 2j sine omega ct. Already jt is there, so finally we'll be getting ts divided by yt sine omega ct. Okay, so this is our h of t. And we have to just try to modify this one to a sync format. So we can do ts pi is already there. Okay, omega is divided by omega c. Already t is there. Just we are multiplying with omega c and dividing by omega c. Okay, then this is sine omega ct. Okay, so this we can write like ts omega c divided by pi sine omega ct divided by omega ct. Why? Because we have to represent in terms of sync format finally. Okay, sync. So sync or sampling function format. Okay, so finally h of t we can write like this. Okay, then once if we know h of t, just we have to apply here. Okay, so what is finally xr of t? xr of t is equal to summation n minus infinity to plus infinite x and ts h of t minus nts h of t minus nts. So now we know what is h of t. Okay, that is ts omega c divided by pi. Okay, ts omega c divided by pi summation n minus infinity to plus infinite x n ts. Again in the h of t, wherever t is there, put t minus nts. So sine omega c t minus nts divided by omega c t minus nts. So this is like finally, if you observe properly, this is sum of many sync functions. Okay, because n can go from minus infinity to plus infinite. This is providing sync pulses. Okay, so finally we are getting sum of sync pulses, sum of sync pulses in time domain. Okay, in time domain we are getting sum of sync pulses. From this actually we can recover back our original signal x of t, that is equivalent to xr of t. Again, once we have to go in detail, okay, we have to draw each and every sync function, then finally we can easily observe that summation value provides the xr of t, that is same as x of t. Okay, thank you.